Have you ever wanted to know what the sun is made of? Let's talk about it in detail and kind of talk about the different layers of the sun. So the best way to think of the sun is like an egg, right? You've got a big hot spot in the middle and these kind of layers around it. Except the whole thing is made of plasma. The layers are all extremely weird, have different things going on, energy moving through them. And yeah, the whole thing is like a few million degrees. So maybe not so much like an egg. Either way, let's talk about the different layers of the sun and see what's going on, what weird things we know of are there. Let's start in the center. You've got the core of the sun, and this is where all of the energy is made. This is where we have our nuclear fusion going on that's, squeezing our hydrogen together to make helium. This area of the sun is about 15 million degrees. I'm using Celsius for this, but at this point, it doesn't really matter what units you're using. It's all extremely hot. So it's like 50 million Celsius, 50 million Kelvin, I think like 27 million Fahrenheit, if you're interested. Either way, if you're there, you're going to die. But energy starts in the core. It's made of plasma, as most of the inside of the sun is. So, it's so hot, it's so high pressure, we can't have solid, liquid, or gas. It changes to plasma instead. And the energy will move from inside the core out to the next region. So the next layer kind of surrounding the sun is called the radiative zone. And this is where the energy kind of moves out of the core and through. The radiative zone is so dense that photons of energy kind of get absorbed and then emitted and then absorbed again and slowly move the heat that way. We call this radiative diffusion. This works the same way as how your cooker works. If you turn the hob on, put a pan on the hob and then put some food in the pan, what happens is the heat from the hob gets absorbed into the pan, and then the heat from the pan will then get absorbed into the food to cook it. This is what radiative diffusion is. So it's things getting absorbed, emitted, absorbed, emitted. If you could follow one package of energy and heat moving through the sun. So let's say it's one photon goes the whole way from the core all the way out of the radiative zone. It's not, but for simplicity, let's just say it is. It would take about 170,000 years for that energy to get all the way from the center out of the radiative zone. So this light that we're getting now is over 170,000 years old. So the next bit is called the convective zone. And this is more energy transfer kind of going on, and this is kind of the last area of the sun that's below the surface. At the point where the radiative zone and the convection zone meet, the sun has cooled to a nice brisk 1.5 million degrees. Again, Celsius, I'm using Celsius for everything. And then when you get up to the surface of the sun, it's about 5,000 degrees. What we have here is a different mode of energy transfer. So whereas radiative is what I told you about, of like your frying pan, the convective zone is more like your radiator in your house. So when your radiator is switched on, what it does is it heats the air around it. The hot air will rise and move around your room. Then it will cool down, drop back down, and move back towards the radiator where it gets heated up and goes round and round and round. We call this a convective loop. The sun is exactly the same. So you have the plasma next to the radiative zone is extremely hot. So it's at about 1.5 million degrees. It rises up to the surface of the sun where it cools down to about 5,000 degrees, passes its heat on, and then will then drop back down again and go round and round and round. So I told you a little bit of a white lie. There's actually another layer between the convective zone and the radiative zone, but it helps to understand the two first before you understand this third layer. And this is called the interface layer, or it's called a tachocline. Because you've got these two different types of energy transfer going on, they can't touch each other. The systems won't work. So radiative transfer requires a certain density of liquid, or plasma in this case. The convective zone requires a different density of plasma. So what you need is some sort of transition period between those two, and that's where the interface layer comes in. The other thing as well is this interface layer is only really been theorized since the 80s. That's a very short period of time, so it's quite a new area of solar physics. When you think we've been studying the sun for about 1,000 years, if not longer, every culture has studied the sun in some way. So to only know about this layer for 40 years, we don't know that much about it compared with the other layers. There are some theories that the interface layer could be where the sun's magnetic field comes from, and we'll talk about the magnetic field a bit more in a minute. So the surface of the sun is called the photosphere, and we think of it as the surface. It's not like the surface of the Earth where you could stand on it. It's still made of plasma, so you kind of sink through it, but we just can't see any deeper than the photosphere. The photosphere is about 3,000 to 5,000 degrees. Now we get into the sun's atmosphere. So the same as how on Earth we have the surface, and then we go up into the air, and you have different layers of the atmosphere. The sun is also the same. The next layer is called the chromosphere, and we can't see this. We look through it, but you can use special telescopes such as a calcium K telescope that can see this layer. So if you want to study it, you can use a special telescope. Now, this is when things get weird. So we've talked about how the sun started cooling down as we're kind of moving outwards. On Earth, if you're standing on the surface and then you go up a mountain, it gets colder, right? So let's say it's 20 degrees here on ground level. And then when you go up into a mountain, you know, it could be -30 or whatever. And it gets colder as you go higher and higher through the atmosphere. The sun doesn't work like that because the sun can't make things easy. Instead, when you get to the chromosphere, it starts getting hotter. The chromosphere, when it meets the photosphere, the surface of the sun, starts off at about 6,000 degrees. And then when you get to the other edge of the chromosphere, you're up to about 35,000 degrees. And then you then move into the next layer of the sun, which is called the corona. The corona is about 1 to 3 million degrees. So you've got the core is extremely hot. It then cools down until it gets to the surface. And then as you move up through the atmosphere, it gets hotter again. We have no idea why this happens. It's one of the big mysteries about the sun. It's called the coronal heating problem. There's a couple of other things I haven't talked about that are called like features of the sun, and these are things that you can see in the different layers. So the most common one that you'll see is called a sunspot. You might have heard of these. These are like little black spots that you can see on the sun. You can see them through most telescopes. You don't need any fancy equipment to see them. Well, other than a solar telescope so you don't blind yourself, but you don't need to see it like, you know, through a massive telescope or anything. And sunspots are just dark spots. They're about 20% cooler than anything else around them, which is why they appear black. When you get these really high temperatures, the changes in temperature affect how things look. So sunspots can have these kind of lines coming off of them that are caused by the sun's magnetic field. And some sunspots themselves are also caused by the magnetic field. So on Earth, we have a North Pole and a South Pole, just like a bar magnet. So you might have done the experiment in school where you get like iron filings, put a magnet on, and you'll see how the iron filings move to the magnetic field lines. This is the same for Earth. Earth has these lines kind of coming from the North Pole going down to the South Pole. The sun is also the same. It also has a North Pole and a South Pole, and these magnetic field lines coming off of it. So where things get weird is on Earth, if you spin the Earth, it takes 24 hours to go all the way around and do a circle and come back. Whether you're North Pole, equator, South Pole, wherever, it's always about 24 hours. On the sun, because it's made out of plasma, this isn't the case. So when you spin the sun, the center, the equator, spins faster than the North Pole and the South Pole. So what that means is when you have your nice field lines, what happens is they'll kind of twist over each other, they'll get all tangled up, and they'll get knotted. So you lose that nice kind of structure. These knots kind of then present themselves as sunspots, and that's where they come from. So when you see these kind of lines coming off of the sunspots, you get these nice big loops. These are the magnetic field of the sun that you can actually see. Depending on how strong the magnetic field line is that gets caught in a sunspot, depends on how big these loops are. So they can just be in the photosphere, or they can go all the way up into the corona. So they can be much bigger than the Earth itself. Sunspots can also appear on their own. So if it's like kind of like a weak magnetic field line that's trapped in there, it'll just be on its own and it'll kind of just go up into the photosphere. They can also appear in pairs. So you get one in the northern hemisphere and one in the southern hemisphere, and the coronal loop will cross the equator. I won't go into too much detail, but coronal loops can then break, which then causes solar winds and then also causes the northern lights that we get here on Earth. If you want to hear more about how the sun causes northern lights, feel free to let me know and I can do a video on that. But yeah, so that's the sun. The sun is very complicated. If you like this video, you might like my last video that was kind of talking about the Hertzsprung-Russell diagram. And this is talking about how we have a graph that kind of maps out the life of stars and the sun. You can know where it's going to be at every point of its life. Anyway, thank you for watching, and I'll see you in the next video.